Okay, while we're getting started, basically what I'm going to talk about is, I guess, less of a manufacturing thing, less of a meter quality thing, more of a how do these meters go in the field, how do we deal with in situ water meter verification, how does it work in practice, and basically what I'm going to do is go through a bit of a list, I guess, of the cock-ups I've made, what I've found that's gone wrong, what's caused me issues in the field, late nights, and generally made my life miserable. Now, I guess all this lines up into in situ water meter verification, but in reality, verification is a two-step process. Now, I split it into validation, verification, and then I chuck another step on top of that, which I call whole system verification, which is taking a usual thing one step further. So I guess we better go through, we'll do some definitions, we'll make sure we're on the same page, we'll look at why each of these things is important, we'll look at how they can go wrong, or how I've found they go wrong, and we'll look at how to fix them. Now, as a bit of a caveat, some of my stuff is going to be based on the field. I've seen something go wrong, I've fixed it, I've fiddled around with things until they've worked. So sometimes it's been a case of I've banged my head against a brick wall of a failing instrument until something's actually happened for me. So first one we're going to deal with, we'll deal with validation. So in most of this, I'm going to be using definitions fleeced out of the Irrigation New Zealand guidelines for water metering. They're available, they're the ones we're operating to for our accreditation, so they're the ones we'll use. So validation, it's a formal inspection, make sure the system, the water meter has been installed how it should be, how the manufacturer says, how your regulations say, how your council says, what you can get away with, and basically it'll depend on what you can read. Now, the interesting thing about this is to do a verification correctly, both your fixed meter and your reference meter must be installed in a valid manner. Now this is a really important thing because usually you'll just rock up, chuck your clamp on, chuck your meter on, get three numbers and run like hell. There's photographs I've seen, you know, the reference meter has been put right next to an elbow, right next to a gate valve, right next to a butterfly valve. It's not a valid installation. So your manufacturer specs, what sort of things are we thinking about here? We're checking just the simple stuff. What's in the book? What's in the manual? You guys do read them, right? Okay. Anyway, sorry. Grounding requirements, meter support requirements, simple stuff. Is the meter designed to be mounted in a horizontal or vertical orientation? I know some multi-jets are only designed for horizontal. What's your power supply requirements? How much noise have you got on your power supply? Have you got pressure limitations? I know some water meters great under pressure, 16 bar. You chuck a couple of meters of vacuum and they're not rated for it. You've got to think about your air relief. Straight pipe requirements, which I think we'll be discussing ad nauseum. And your full pipe requirements. I mean, you've got to think about, for some of your meters discharging into a pond, for example, you've got to think, is my pipe actually full? And on top of that, anything else the manufacturer thinks is important, which really means read the manual. It's actually got some useful stuff in it. Okay, so just a quick example of something that you might find in the manual talking about, you know, this case, disturbance distances from fittings. Again, I've fleeced this from the INZ guidelines. It's not super clear here, but what we're going is basically the length of straight pipe required for different installations. So you've got your standard 10 and 5, then you go up, you've got spiral flow, you've got 50 diameters upstream, downstream. I think this one actually is for an insertion meter. It's quite conservative. In some cases, it's a heck of a long way. Recommending 50 diameters. If you've got a 100 mil pipe, 50 times 100 mil, that's about 5 meters of straight pipe upstream. That's a massive headworks. Okay, again, it varies from meter to meter. You can do some tricks. You can chuck some flow straighteners in. Again, now you're moving outside what the manufacturer is saying, which is where we probably come into this whole type certification thing we're dealing with. Just an example. Now, why is this important? Well, why do we have to follow the manufacturer's guidelines? Usually it seems to be that most of the things around a water meter are involved in reducing turbulence. Most water meters seem to operate on the principle they don't actually measure flow rate, they don't actually measure flow volume. All they do is they measure flow velocity. Then by some clever K factor, some clever math going on inside that unit, they convert that to a volume or a rate that you can then read on the display. So the critical thing about that is any time a water meter gets that velocity profile interrupted, your reading goes out of whack. I mean, you can see the example here. You've got nice laminar streamlines up here. If you were to take an average across that flow there, you're going to get a fairly passable representation of what's going on with the velocity. You try doing that in the bottom section, and the flow is chaotic, it's turbulent, you're not going to get an accurate velocity reading, and therefore you're not going to get an accurate flow reading. Turbulence, basically, I see that as the number one enemy of any water meter installation. Again, just some quick examples of streamlines. What you're getting downstream of a partially closed butterfly valve. Again, what you're getting, again, butterfly valve. And another example of downstream of a wafer check valve. And you can see that turbulence persists downstream. Now, what does a valid installation look like? It's going to have a lot of straight pipe. It's going to have bends a long way away. It's going to have a situation where you've got a nice uptick to make sure the pipe's full. This is just one of the examples here. You can see I've got enough straight pipe to also fit my reference meter in line. So this is really, really good. This is what I like to see when I go out to do a verification, because I know something is going to happen. Again, another example. This has got a few more water meters in it, but again, the same thing. I've got a lot of straight pipe. I've got air release. I've got the butterfly valve and the check valve downstream. Some people might recognise this installation. But again, it's a really good example of how to do it right. So we move on. We go from right installations to marginal installations. This installation here, it's a good install. We've got 5 and 2, so we've got enough straight pipe to get away with it. We've got a check valve upstream. Okay, we can usually get away with that. They don't usually throw too much turbulence. Well, they don't seem to cause me any problems. But we're in an issue here where I've got nowhere to install my reference meter. 10 and 5, if I try and get this to recan as it is, I'm going to have a fight. So what we need to do here, we need to start talking with the council. What's acceptable for our regional council? Can we get this approved somehow? The way we go about that, we'll try and go for a non-standard headworks approval. We'll find somewhere else to put the reference meter. We'll make a bit of a case that we can do this correctly. We'll then bundle it all up, and with a very nice letter, some negotiation skills, and we'll see if we can get that through regulatory approval. Depending on whether or not the requirements for that regulator are stringent or not, you might get it through. Otherwise, you're left with a redesign of your headworks. In other cases, well, there's no hope. There is a water meter in there. No, it wasn't reading right. You've basically got no chance. The flow in this system goes in this bit of flexible hose here, downhill through the meter to a free drain here. So not only is the meter not installed with straight pipe, it doesn't have a full pipe. It's got a valve just upstream of it, and it's also carrying raw effluent from a chicken processing plant, just to make life even more entertaining. This basically was abandoned hope. So in this sort of case, you just reinstall the meter, because usually the meter's still going to be reading fine if you actually give it a chance. Again, a couple more examples. Usually it's the small stuff, because someone's bought their own water meter and they've chucked it in to save themselves a few dollars. Again, the only thing you can do here, you just say very nicely, "I'm sorry, sir, your meter isn't valid, and we'll start again, please." And they look at you and say, "But I was told it was okay," and you smile and say, "Well, I think you probably want to hire someone else to do your verification." So, in summary, what does a validation do? Ensures the meter's installed correctly. It's a critical part of ensuring that a meter can be verified. And alone, it does not ensure that that meter is reading correctly. I could have a valid installation of a meter that's failing. Is that going to verify? Simple answer, no, it's not. So, we've established that validation alone isn't going to prove that our meter is reading correctly. We've also established that both our fixed and our reference meter need to be installed in a valid manner to enable us to carry out our verification. So moving on, we now get into verification, in situ verification, that one that everyone usually prefixes with a bit of swearing. Again, we're going down the same path, definitions, why we do it, and now I'm going to dig into some of the reasons why it goes wrong for me, what I've done to fix it, and how I cope with doing in situ verifications. So verification, again, we throw out the INZ definition of it, formal inspection and testing of the water metering device or system to prove and document that it meets the accuracy requirement of the regulations. So what we're doing here, we've got some keywords. We've got test, we've got prove, we've got document. So we have to test, prove and document. Very critical thing. So why do we verify? Well, I think that's been covered off pretty well, but I'll reiterate it. If you don't verify, you have no idea if the numbers you're getting back are accurate. For us, That's really important because we take some pretty important decisions around that. We provide decision support, we do resource management applications off the back of these. We potentially will be going to court on behalf of our clients on the basis of the data being provided by their water meter. That's something we probably want to get right, or otherwise we're going to be looking pretty stupid. Furthermore, on the other side of it, it provides evidence of whether we're underutilising or not. For our clients, it's in their best interests. They want to use all the water that's allocated to them. If their meter's over-reporting, they're underutilising. That's dollars that they're wasting. So, where can it go wrong? The challenges to a successful verification. Well, in a summary, pretty much everything. If it can go wrong in a verification, it probably will at some point in time. But we can sum it up pretty nicely. We've got our non-valid installation. So, usual pipework problems, turbulence, someone set the meter up wrong. The setup may have changed. We might have got some rust build-up, your scale in the pipe, that sort of thing. Operator error. We might have actually just stuffed up our verification. There's that 1% which I'll get into, and there's also the problem of selection bias, which I need to discuss as well. So your post-install changes, your corrosion, someone's chucked a blooming backflow preventer in there, someone's decided to chuck a booster pump upstream of you without telling you. Yes, all these things have happened to me. Your water meter's worn out, it's blocked, it's had sand through it. Interestingly enough, I've pulled out meters, mechanical meters full of sand. They're pretty hard to turn. We've pulled out old mag meters. They've been in for about 20 or 30 odd years, but they've been used for effluent, and the aggressive media has finally corroded the inside of them out. But 25 or 30 years is probably a pretty good run. So corrosion. Here's a good example. Again, your standard rusted pipe. This gives you turbulence inside the pipe. If you're using a clamp on ultrasonic, you're going to really struggle to get a thickness reading. In fact, you're probably not going to get one at all, or it's going to be all over the show. One of the clues is if you're using an ultrasonic thickness gauge for your measurements, you're going to be up, you're going to be down. Your reading is going to fluctuate between, say, 4.5 mil up to, say, 10, 15 mil. You're going to get wildly varying readings, and you're going to start wondering what the heck your thickness gauge is doing. Some clamp-on meters are going to complain about this. Some are going to say, well, no, I don't get a signal. Some of them are going to faithfully report you the wrong number with no errors, and you're going to be completely oblivious. Without looking inside the pipe, you're not going to know what's going on. That's a problem. Does it get better with a rig or a volumetric calibration? Well, sort of, because you're adding your own pipe work, so you don't have the problem with your verification meter, but it's still going to play hell with your fixed meter. Back one. Okay, going back, you've got water meter wear or damage, you've got your aggressive media, something's broken in the water meter, something's damaged that you can't see on an obvious visual inspection. Again, you've got simple stuff, your mechanical meters, they'll block, the dials will move erratically, you'll see that the actual gauge dial will jump instead of turning smoothly. Your mag meters, they may report a diagnostic fault, they might not, depending on the model, depending on the brand, depending on what's gone wrong. Sometimes they'll report garbage. Sometimes you get flow spikes. Sometimes it'll go to full scale and you'll wonder why until you realise that when you screwed the cap down, you pinched one of the vital sensor wires. So now you're left trying to solder it back together again. So, again, your water meter can fail. There's all sorts of different ways that they can fail. The list is exhaustive, but either way, it's going to make your verification difficult. So now we'll drill into some of the ways we can actually carry on that verification and how they can fail. Again, it's a bit negative. This is all about how things break. So we've got the three main methods. Your clamp on ultrasonic, your reference meter in series. Now INZ also pulls out the insertion meter. I put it back in there because I just call it another series reference meter. I don't deal with it any differently. Andrew's going to shoot me for that. And we've also got the old faithful volumetric. So clamp on ultrasonic meter. Here's just a couple of them where we're having a bit of a play. And again, you know how they operate. You measure up the pipe, you clamp them on, you check your signal's good. They send a signal through the pipe that measures the velocity. You've told it the thickness, you've told it the dimensions, and it works out what the flow is from that. You take a lot of measurements, you're taking a lot of readings. So there's some key things with this. There's a lot of places that you can have operator error. There's a lot of places you can make a stuff up, which is going to affect your readings. As you've just been seen, I've done the same calculations here. If you've got a 100 mil schedule 40 pipe, It's got an ID of about 102 mil according to the table. If we assume 100 mil nominal bore, program up a meter with that instead, we've got about a 4% difference in our flow readings. That's enough to throw your verification off right there. Measuring close enough is not good enough. You take the measurements accurately, you're going to get an okay verification. You forget your thickness gauge, you assume, you rely on your tables, it's not going to work. Measure everything. Double check it. Did you read it right? Take the measurement in a couple of places. Is it consistent? Once you've got your measurements, make sure you know how to put them into your device. Make sure you know how to program it. Make sure that you can actually get that working. I mean, heck, shout your supplier a bear and go and find out what they know about it. Moving on, series flow meter. This is your rig. This is old school. This is one of our old units. This is before mags were even around. This is actually a mechanical rig we use for aquifer testing. The principle's the same though. You bring your own headworks, you take your meter, or you mount another meter in situ. You're basically bringing another accurate meter along to check your other meter. It's great. It's the same principle as a clamp on ultrasonic, except you don't have that setup issue. So where can a series flow meter go wrong? Well, sorry, let's go back a step. The series flow meter, you need to have specific plumbing. This makes it a real pain in the neck for those quick and dirty verifications where you just need to get in, get out, and nothing's been set up for you. You've actually got to think about setting up a series flow meter before you do it. This adds cost when you're selling a headworks, when you're selling a water meter. The last thing you want to do is add those extra fittings to mean that the next guy down the road's going to beat you out on that particular job. So there's an element of cost associated with getting this right. And that's probably the biggest challenge around setting up a rig, is getting a situation which works for you when you do a rig that doesn't involve you carrying around an entire irrigation warehouse worth of parts and fittings to make every damn setup compatible on the planet. You've got to find a hydrant, off-take, do some spanner work. They are a lot more work to do than a clamp on ultrasonic. The trade-off is more accuracy. The other thing you've got to be careful about is making sure you've actually sized your rig appropriately. There's no point using a 50mm meter to verify a 200mm bit of pipe work. It's not going to work. Your turn down's way too low. Other thing though, they're less prone to error, but you still get leaks, you've still got off-takes. You've also got the problem if you've set up your rig on a hydrant that's 300 metres away from your pump shed, you've got a lot of running to do between your two sites. How do you know you've taken those readings right? Easy enough, you put a data logger on so you can get around it, but it's something again you've got to think about before you actually get on site. Or you have an apprentice do the running for you. Last one, the one I really like, if you can use it, is your volumetric. The good old-fashioned bucket and, calibrated bucket and stopwatch. A 20 litre Mitre 10 bucket doesn't work. You need to check it. Simple principle, you run water through the bucket, run water into the bucket, time how long it takes to fill, lather, rinse, repeat. This is actually prone to the same problems of your clamp on ultrasonic because it's prone to errors in measurement. You make assumptions about your volumes, you're going to get the wrong results. However, you can use really big buckets. A 50,000 litre RX tank is the perfect bucket if you're pumping out of it. What I also like about the volumetric method is it's a great backup plan. If you, for example, have reason to distrust your clamp on ultrasonic, if you've dropped your clamp on ultrasonic and it's got wet and it's failed on you and your client still wants a result, you can get something and you can get a good, valid verification out of it. So here's a good example of it. This was actually a stuff-up I made. I've got a little insertion meter down here. I'm probably a bit skint on straight pipe here, but I had a bit down here that I had to dig around, and I found a good length of straight pipe I could work off. But my verification meter had gone for a swim the day before, and I thought, I'll dry it out, it'll be fine. Turns out it wasn't, it died, and I'm 3 hours from home. Fortunately, this system was pumping out of a nice tank that I could get the dimensions of, and I could work out the change in volume over time. So what I did, I measured the circumference of the tank, measured the wall thickness of the tank, worked out the cross-sectional area, and then just did the change in depth over time as the pump was abstracting from it. That gave me an average flow rate. I could then compare that to an average flow rate reported by the water meter over the same time, and from that I could get a verification that passed and was acceptable by ECAN. I had to document the heck out of it because it was non-standard and I needed to explain my working, but it worked. Okay, having said that, your volumetric, it's still going to go wrong. You've got to measure your vessel. Now, one of the tricks, and this was one I think Horizons used, was actually use a set of scales, hang the whole shooting box off a tractor, and don't worry about measuring your vessel, just put a set of scales at the top of it, and instead of measuring your volume, measure the weight. All good. I mean, you've got to be careful because you're adding a ton of weight to the extremities of a tractor, so you want to just check you've got your numbers right before you add the weight, I imagine. But again, perfectly good. You've got another issue too around flow timing. Trying to fill a 20 litre bucket with a 40 litre a second take probably isn't going to work. Similarly, trying to fill a 5,000 litre tank with a litre a second flow rate, you're going to be there for a long, long time. So again, it's about sanity checking these things. And then there's that 1%. VSD interference, that's been talked about. I mean, I've had situations here where I haven't been able to run a laptop in a pump shed simply because there's been too much interference from a poorly grounded variable speed drive. We've had issues reported, and I still don't quite understand these, around pipe galvanising affecting clamp-on ultrasonics. I don't understand this one. I don't pretend to. If someone here knows more about this than me, I'd like to talk to you at the end of this show. I don't know if I can put it down to galvanising or some other cock-up I've made. I don't know enough about it, and I haven't got any proof either way. Basically, the one concern I have is how often have I gone looking for something wrong with the system when it's just me that's made the stuff up? How many of these so-called failures have we got are purely down to operator error or not understanding the equipment correctly? I can't answer that. I know I've done them. I know I've had some where I've scratched my head until I realised I've read the tape wrong, which is really embarrassing, by the way. That's why you need plan B. If you can't get it one way, have a look another way. Try another reference meter. Try your volumetric method. Just have a plan B. Always have a get out of jail free card if you can play it. And then we get to the last part, which I don't have an answer to, selection bias. How many times have we tried to verify until we get the answer we wanted? Oh, yep, she's right, let's go home. After you've tried a dozen times to get the right reading. What makes that last reading you got more accurate than the half dozen or more that you did before then? Because it agrees with the fixed meter? Well, hang on, we're trying to prove that the fixed meter's right. Is that really a valid way of doing it? Well, my answer is no, but how do we get around it? I don't have an answer for that, except maybe limiting the number of runs you're allowed to do your verification. So just to sum up how we can get things wrong so far, operator error. That's a really big one. Making a mistake yourself, not understanding the gear, reading something wrong. Invalid installations, making sure you've installed everything correctly. If you don't have the documentation for your water meter, or if the water meter wasn't supplied with documentation, my first rather cynical response is you probably need to buy a better water meter. The more sensible response, if you don't have a choice in that water meter, is have a look at the INZ guidelines. I understand they are worst case scenario, so they're probably a good starting point to work with. If not, yeah, you probably want to try and pick meters that actually have those guidelines associated with them. Measure your critical dimensions. Don't assume anything. If you assume it's Schedule 40, well, do you know if it's Schedule 40? I know of a particular case where someone went to do a measurement on a clamp-on ultrasonic. Someone had painted the PVC pipe silver. So they were using the clamp-on ultrasonic settings for galvanised steel. I'm not joking. If you're not certain, cross-check it with another method. Always have plan B. So, to summarise, validation. Has it been installed right? Verification. Is it reading accurately? They're both critical. They tie in with each other really nicely. We've still got the problem of how much verification are we willing to pay for. I spent an entire day trying to get a system to verify up. It didn't. Now we move on to the next side of things. Whole system verification. This is a bit of a step beyond our regular water meter verification, but in reality, this is one of the areas where I lose the most sleep and I get the most inquiries. And to be honest, for me, it's one of the hardest parts to deal with because, well, you'll see there's a lot of stuff that goes on in this. The water meter isn't the only part of the water measurement system. That water measurement system may include a data logger, a PLC, several display interfaces, several transfers of data between various providers before it actually reaches your consumer, your client, as a final product. That water meter is a portion of a chain of devices. At each stage in that chain, you could have something happen to that data, you could have something happen to your flow rate, and you could change that data from what it was originally. Therefore, to ensure that a system is working correctly, you need to check from the meter to the logger to the data management system right through to that end product to answer, is this data being delivered to my client correctly? How do you do this? It's actually not that difficult, because no matter how complicated the system, you treat it as a black box. You say, I am putting this flow rate in, I'm getting this flow rate out. You don't care whether that's being sent through 4, 5, 6 providers. You don't actually care what's being done to that data. All you need to do is, when you're doing your verification, run your meter up for half an hour. Most systems are set to log every 15 minutes. If you run a system for half an hour, you're going to catch at least one 15-minute log interval. Then all you do is check the telemetry page, check the data logger, make sure that that's actually displaying the same flow rate the water meter is reading. If those two numbers line up, you're good to go. Now, interestingly enough, the National Environmental Monitoring Standards specifies a 1% tolerance between your meter and your logger for QC 600 data. That's a really good starting point, because quite frankly, if your meter, which is collecting data and sending it, doesn't line up with the endpoint, you've probably got some pretty major problems. This isn't part of the official verification process, but if you do it, it will save you a heck of a lot of time and a heck of a lot of grief and a heck of a lot of please explains down the track. So, what can go wrong? Simple answer, lots. How many people are touching the data before it gets to the client? At least every time someone touches that data, something could go wrong with it. So, we need to go through, we need to check. We need to check the water meter sending pulses correctly, we need to check the loggers getting the pulses correctly. We need to check that those pulses are sensible for the flow rates. Now, again, the NEMS says the pulse outputs must be able to resolve to 1% of normal hourly volume. Well, that's a pain in the neck to work out in the field. So for 72 cube an hour, which is roughly 20 litres a second, we go for a pulse per 100 litres. In practice, that works out that when the system's running at its production rate, you want to be doing around a pulse every 5 to 10 seconds, give or take. And that seems to give you enough pulses that you can count them, you can see what's going on, but not enough that your system's overloaded and counting too high. But what you'll find, pulses can be missed, they can be added, they can be scaled wrong. That pulse output is actually quite susceptible to interference. So we can get, of course, our lovely free and variable speed interference. Electric fences are great. They can interfere with both the meter and with the pulse. I've had a system that I've tried to verify that I had to put in 4 extra grounding stakes and another ground onto the groundwater bore before I could stop the system reading 6 litres a second with all the valves closed. It was a grounding issue with the electric fence. The electric fence ground, for some reason, wasn't playing nice with the shed ground, and it took a fair bit of messing around to get it. Meter compatibility. Interesting one, this. Open collector versus dry contact. Different types of pulse output. They're not all created equal. You need to make sure you understand what type of pulse output it is, how to deal with it, and how to make sure that whatever data logging system you're using is compatible with the output that your meter provides. Power supply issues is another good one. I've just had one recently where we've got a system where the water meters are reading perfectly, they're working fine, they're delivering a pulse fine. There's an interface between the water meters and the telemetry system that involves a series of solid state relays. The power supply to those solid state relays is not a happy power supply, and we've now got a system which sends the pulses out, gets to the solid state relays, and every 3rd or 4th pulse gets through and the rest are missed. And we've got the other one, of course, where it just plain hasn't been wired in properly. So they've wired the pulse into the analog or something like that. Again, yes, it does happen. If it can go wrong, it probably will. So how do I fix it? You've got to be systematic. You start at one end, you start at the water meter, and you just work your way through the chain, making sure every step of the way is correct until you get to the end. It's a rigorous process. It's a pain in the neck, especially if you're dealing with a system where you've done the water meter, someone else has done the telemetry, and someone else is hosting the data. You've got to talk to a lot of people all at once, and you've got to convince them that, yes, I do need to look at your system, and yes, we do need to make sure it's not your part, because the usual response you'll get is, not me, mate, my system's working fine. Because, of course, your system always works fine, and you never make a mistake. So in summary, to work through this, you measure, check again. Don't assume. Be a little bit paranoid when you approach these systems. As I said, it may effectively lie to you. You might not have any error messages telling you something's gone wrong, and you may have made a mistake. It happens. I know I do. Know your system. Know the equipment it contains and what its limitations are. Follow any guidelines you've got, because they're usually there for a good reason. If a meter manufacturer says 50 diameters downstream from a swirling flow generator, from say a partially closed butterfly valve, there's a good reason for that. Take the time to get the correct result, because it will pay dividends and keep the hair on your head. So basically that's what I've got to talk about. That's some of the stuff I've found. There's some issues there which I've raised which probably we need to talk about and work out how we're going to deal with them. There's some things we have to go through. Are we conflating validation and validation? Oh, no, validation with verification. I don't know. I think we are, because I think the two are separate. Do we need to be focusing more on whole system verification rather than just making sure the numbers in our pump shed line up? Because when in reality the numbers in the pump shed aren't what's going to get you in trouble. It's the numbers that are sent to the council. Are there really any bad meters? Are we just a bunch of poor workmen blaming our tools? I'm being controversial, Andrew told me to. And cost versus accuracy. I mean, how much accuracy, how much time are we actually willing to spend going through this and making sure that our system's accurate? Is there a point where we're just into the law of diminishing returns and we're just pouring good money after bad to get a further 1% of accuracy? I mean, like I said, most systems you can get a very accurate verification. You get the whole headworks, dig it up, stick it on a truck, send it to an accredited laboratory, verify the entire system in the lab, and then pay for the cartridge. So, there's some questions. They are a little bit controversial, I hope. What do you think?